Good morning. This is Angie McDonald. I'm your instructor, and what I'm going to do for this module is try to narrate some of the material you're going to be covering in order to give you an opportunity to better understand it. What you're looking at here is a diagram of a permanent magnet. There are three types of magnets: permanent, resistive, and superconducting. We're going to concentrate mostly on permanent and superconducting. This diagram shows a square. That square is an iron yoke, a big square of iron. It is holding together individual ceramic tiles that have been magnetized. If you look at the picture on your right, you see Dr. Bouchon magnetizing these ceramic bricks. The form itself is of magnetized, individualized ceramic tiles. This is what we consider a permanent magnet. If you've ever seen a permanent magnet, these are traditionally your open type of magnets. What I took here was a picture of a Hitachi or a Hitachi Aries magnet, and I put Dr. Bouchon's picture on top of it to give you an idea of where these ceramic bricks lie in an actual permanent magnet. So what are some advantages and disadvantages of permanent magnets? First of all, advantages: very low electricity use. They're extremely stable magnets. There's no changing the strength from one end of the magnet to the other. The low magnetic fringe field. In other words, you can put it with very little shielding. You don't have to have as much massive concrete and steel on the walls. Disadvantages: it is on. It is permanently on. Unless you disassemble each and every brick, it is on. You can't quench it. They're extremely heavy, so the concrete has to be properly weighted. And for the most part, they're not very powerful. Now, what I'm sharing with you is traditional permanent magnets. There are some new ones coming out now from Philips and Hitachi that are much more powerful. They are 1.0 to 1.2 Tesla magnets. They are superconducting. They're a completely new generation. They're not on your ACR registry at this point, so I'm not going to cover them. Another type of magnet is the resistive electromagnet. Now I'm going to share this briefly because they're no longer in use. What you're seeing in the two center circles are two large magnetic rings that produce the magnetic field itself. They're responsible for the main magnetic field. The two smaller rings, one on the front and one on the back, help keep the magnetic field uniform. The problem with these magnets were they had to constantly be plugged into an electrical outlet. So imagine, if you would, your home electricity bill amplified 100 times fold just to do an MRI. It was extremely expensive. So what happened was engineers went back to the table to try to figure out how to keep this very powerful electromagnet on but not require a permanent electricity source. Now, there were some advantages to this. First of all, you can turn off the magnet with a switch. Literally, come in for the day, you turn the magnet on, it ramps up, turn it off when you leave. The advantage was that it had a low magnetic fringe field. In other words, the magnetic field beyond the bore of the magnet, that's what we mean by fringe field, beyond the bore of the magnet. It didn't extend very far, so the magnet was very well contained. A disadvantage was that it required constant electricity. Again, think about your home electricity bill. Imagine 100 times fold just to get an MRI of the brain out. It was a significant cost. There was no break even there. It also required a water cooling system. And the magnetic fields still were not as powerful as we would have liked. The stronger the magnet, the more signal you could get from the tissue. The more signal you can get from the tissue, the better image resolution you can get.